Table B.310.6 of the National Electrical Code applies to underground duct bank installations with 3 conductor cables. The reason the smallest cable size presented in this table is 8 AWG is due to the limitations of smaller gauge conductors when installed in underground environments. Specifically for conductors smaller than 8 AWG, such as 10 AWG, 12 AWG, and 14 AWG, the thickness of the conductor insulation is generally insufficient to provide robust protection against the harsh conditions associated with underground installations. These conditions include exposure to moisture, corrosive elements in the soil, mechanical stress from shifting earth, and potential damage from rodents or other pests. The National Electrical Code mandates minimum insulation thicknesses and protection methods to ensure the safety and reliability of electrical installations. The insulation thickness of smaller gauge conductors might not meet these minimum requirements when subjected to direct burial or duct bank installations without additional protective measures. Therefore, the code typically restricts the direct underground burial or duct bank installation of 10 AWG to 14 AWG cables unless they are provided with supplemental protection such as being installed in a conduit or raceway system. This additional protection acts as a barrier, shielding the cables from physical damage, moisture ingress, and chemical exposure, thereby extending their lifespan and preventing electrical failures. For smaller cables such as 16 AWG or 18 AWG, or even smaller conductors which may be necessary for specific low-voltage applications, the National Electrical Code requires that they be installed within an approved raceway or other suitable method of protection when routed underground. A raceway, such as rigid metal conduit, intermediate metal conduit, electrical metallic tubing, or rigid polyvinyl chloride conduit, provides a continuous, enclosed pathway that protects the conductors from physical damage and environmental factors. Other approved methods of protection may include direct burial cables specifically designed and listed for underground use, which have enhanced insulation and jacketing to withstand the rigors of the underground environment. These direct burial cables are typically identified by markings on the cable jacket indicating their suitability for direct burial applications. The requirement for additional protection for smaller gauge conductors stems from their increased vulnerability to damage. Smaller conductors have less mechanical strength and are more susceptible to being cut, crushed, or abraded by rocks, roots, or other objects in the soil. Their thinner insulation also makes them more prone to moisture absorption and electrical breakdown, which can lead to short circuits, ground faults, or even fire hazards. By requiring the use of raceways or other approved protective measures, the National Electrical Code aims to mitigate these risks and ensure the safe and reliable operation of electrical systems installed underground. When selecting a raceway for underground cable installations, it is important to consider the specific environmental conditions and the type of soil present at the installation site. For example, in areas with highly corrosive soils, it may be necessary to use a raceway material that is resistant to corrosion, such as rigid polyvinyl chloride conduit or coated metal conduit. It is also important to ensure that the raceway system is properly installed and sealed to prevent moisture from entering the conduit and damaging the conductors. In addition to providing physical protection, raceways also offer the advantage of allowing for easy access to the conductors for maintenance, repair, or future modifications. By installing the cables within a raceway, they can be easily pulled out and replaced without having to dig up the entire trench. This can save time and money in the long run. When installing cables in a raceway, it is important to follow the National Electrical Code guidelines for conduit fill, which specifies the maximum number of conductors that can be installed in a given size of conduit. Overfilling a conduit can make it difficult to pull the conductors and can also damage the insulation, leading to electrical problems. The National Electrical Code also provides guidelines for the proper spacing and support of underground raceways to prevent them from sagging or shifting over time. These guidelines help to ensure the long-term reliability of the underground electrical system. In summary, while Table B.310.6 of the National Electrical Code focuses on 8 AWG and larger conductors for underground duct bank installations, smaller gauge conductors can be used underground provided they are installed in accordance with the code requirements for additional protection. This typically involves the use of a raceway or other approved method to shield the conductors from physical damage, moisture, and other environmental hazards. By following these guidelines, it is possible to safely and reliably install smaller gauge conductors underground for a variety of applications. Furthermore, it's important to consult with a qualified electrical engineer or contractor to ensure that the specific installation meets all applicable codes and standards. The National Electrical Code is a comprehensive set of regulations that are constantly updated to reflect the latest advancements in electrical technology and safety practices. Staying informed about the latest code requirements is essential for anyone involved in the design, installation, or maintenance of electrical systems. In addition to the physical protection provided by raceways, it is also important to consider the ampacity of the conductors when designing an underground electrical system. Ampacity refers to the maximum amount of current that a conductor can safely carry without exceeding its temperature rating. The ampacity of a conductor is affected by several factors, including the size of the conductor, the type of insulation, the ambient temperature, and the number of conductors installed in the same raceway or cable. The National Electrical Code provides tables that list the ampacities of various types of conductors under different conditions. These tables should be consulted when selecting conductors for an underground electrical system to ensure that they are adequately sized to carry the anticipated load. If the conductors are undersized, they can overheat, which can damage the insulation and lead to electrical failures. In addition to ampacity, it is also important to consider the voltage drop in an underground electrical system. Voltage drop refers to the decrease in voltage that occurs as current flows through a conductor. Voltage drop is affected by the length of the conductor, the size of the conductor, and the amount of current flowing through the conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code recommends limiting voltage drop to a certain percentage of the supply voltage. To minimize voltage drop, it is important to use conductors that are adequately sized for the length of the run and the amount of current being carried. It may also be necessary to use larger conductors or to install additional voltage support equipment in some cases. Proper grounding is another critical aspect of underground electrical system design. Grounding provides a low impedance path for fault current to flow back to the source, which helps to protect people and equipment from electrical shock. The National Electrical Code specifies the requirements for grounding underground electrical systems, including the size and type of grounding conductors, the location of ground rods, and the bonding of metallic components. It is important to follow these requirements carefully to ensure that the grounding system is effective in protecting against electrical hazards. In addition to the National Electrical Code, there may be other local codes and regulations that apply to underground electrical installations. It is important to check with the local authorities to determine what these requirements are and to ensure that the installation complies with all applicable codes and regulations. Underground electrical systems offer several advantages over overhead systems, including improved aesthetics, reduced risk of damage from weather events, and increased security. However, they also present some unique challenges, such as the need for additional protection against moisture and physical damage. By carefully considering these challenges and following the guidelines in the National Electrical Code, it is possible to design and install underground electrical systems that are safe, reliable, and long-lasting. In the context of the initial question regarding Table B.310.6 and the minimum conductor size of 8 AWG, it is crucial to understand that this table is specific to underground duct bank installations with 3 conductor cables. The ampacities listed in the table are based on specific assumptions about the thermal environment and the spacing between cables. If the installation conditions differ from these assumptions, the ampacities may need to be adjusted accordingly. For example, if the cables are installed in a duct bank with closer spacing, the ampacity may need to be derated to account for the increased heat buildup. Similarly, if the soil surrounding the duct bank has a high thermal resistivity, the ampacity may need to be derated to account for the reduced heat dissipation. The National Electrical Code provides guidelines for derating ampacities under various conditions. These guidelines should be consulted when designing an underground electrical system to ensure that the conductors are adequately sized for the specific installation conditions. It is also important to consider the future load growth when designing an underground electrical system. The conductors should be sized to accommodate the anticipated load for the foreseeable future to avoid the need for costly upgrades later on. In some cases, it may be more cost-effective to install larger conductors initially to provide for future load growth, rather than having to replace them later. Proper documentation is essential for any electrical installation, including underground systems. Accurate records should be kept of the location of all underground cables and raceways, as well as the size and type of conductors used. This information will be invaluable for future maintenance, repair, or modifications. The documentation should also include details about the grounding system, including the location of ground rods and the bonding of metallic components. The documentation should be kept in a safe and accessible location, such as a building management office or a central records repository. Regular inspections and maintenance are essential for ensuring the long-term reliability of underground electrical systems. The cables and raceways should be inspected periodically for signs of damage or deterioration. Any damage should be repaired promptly to prevent further degradation and potential electrical hazards. The grounding system should also be inspected regularly to ensure that it is functioning properly. The ground rods should be tested to verify that they are providing adequate grounding impedance. The bonding connections should be checked to ensure that they are tight and corrosion-free. By performing regular inspections and maintenance, it is possible to identify and address potential problems before they escalate into major failures. This can help to extend the lifespan of the underground electrical system and minimize the risk of electrical hazards. Finally, it is important to remember that electrical work can be dangerous. Only qualified and experienced personnel should perform work on underground electrical systems. All work should be performed in accordance with the National Electrical Code and other applicable safety standards. Proper personal protective equipment should be worn at all times, including gloves, eye protection, and appropriate clothing. The work area should be properly barricaded and warning signs should be posted to alert others to the hazards. By following these safety precautions, it is possible to minimize the risk of electrical accidents and injuries. In conclusion, the minimum conductor size of 8 AWG in Table B.310.6 of the National Electrical Code for underground duct bank installations is related to the insulation thickness and protection requirements for underground cables. Smaller gauge conductors can be used underground, but they must be installed in accordance with the code requirements for additional protection, such as being installed in a raceway. Proper design, installation, and maintenance are essential for ensuring the safety and reliability of underground electrical systems. Consulting with a qualified electrical engineer or contractor is recommended to ensure that the specific installation meets all applicable codes and standards. The National Electrical Code is a valuable resource for information on electrical safety and best practices. Staying informed about the latest code requirements is essential for anyone involved in the design, installation, or maintenance of electrical systems. Remember that electrical safety is paramount, and all work should be performed with caution and in accordance with established safety procedures.